Bismillahirrahmanirrahim. I welcome you to the 22nd lecture for the series of lectures on advanced computer architecture. Today, we will continue our discussion onto the instruction level parallelism. After a brief recap of what we discussed last time, I will discuss some techniques to eliminate computations for dependence. We will also discuss some 3 new techniques, namely the software pipelining, trace scheduling, and superblocks to minimize or uncover instruction level parallelism. Last time, we extended our discussion on the static scheduling with very long instruction word processors. We highlighted very long instruction word as a word format which is a format for long instructions, or it is a fixed instruction packet with explicit parallelism amongst the instructions in the set of instructions in the packet. The multiple operations are initiated in a cycle by the compiler, which places these instructions in a packet. Wider processors having multiple independent functional units are used to eliminate recompilation by the compiler, and the compiler finds dependence and schedule instructions for parallel execution. It results in the improvement as compared to the superscalar processor in respect of these 2 parameters, that is the average issue rate, which is the number of operations issued per cycle, and the execution speed, which is the time to complete the execution of a code. However, the efficiency of very long instruction word processor, which is measured in terms of the percentage of available slots containing an operation, it ranges from 40% to 60% in case of very long instruction word processor, which is in fact slightly underuse of the resources available. However, following this, we also distinguished between the instruction level parallelism and loop level parallelism. While talking about the loop level parallelism, we found that the loop carried dependencies, they prevent loop level parallelism, but they do not affect the instruction level parallelism. At the end of our discussion last time, we studied the affine-based greatest common divisor algorithm to detect dependence in a loop. Then, continuing our discussion, we exploited how a compiler can reduce the dependent computations. Today, we will continue this discussion, and we will find out some new methods to reduce the computations for dependence. For this purpose, let us first of all consider a technique known as copy propagation. Now, this approach is used to simplify and optimize the code in a very long instruction word or for instruction level parallelism. For this purpose, In order to understand the concept, let us consider this example over here. In this example, we use two add instructions to add a number 4, such as first we add a value 4 into the register R2 and place this value into register R1, and then we add a value 4 again in register R1, and this way overall we add a value 8 to the present contents of register R2 and place the result in R1. Here the net use of R1 is to hold the result of the second add instruction. Therefore, we can make use of substitution, and we can substitute the result of the first add operation into the second operation by using one single instruction, that is add R1, R2, number 8. Here we have eliminated the multiple use of register R1 during loop unrolling. Particularly in case of memory access, this technique of reducing computation eliminates the multiple increments of array indices during the loop unrolling, and at the same time to move increments across the memory addresses. This copy propagation technique reduces the number of operations or the code length. Now we will talk about the optimization to increase parallelism of code. However, the optimization is possible by restructuring the code that may increase the number of operations while the execution cycles are reduced. Such an optimization is referred to as the tree height reduction, because it reduces the height of tree structure representing a computation and making it wider but shorter. I will discuss this with the help of this example over here. In this code sequence, you can see that we have got 3 add instructions. Therefore, it requires 3 cycles for the execution, because here all the instructions depend on immediate predecessor and cannot be issued in parallel. Therefore, let us see that how we can take advantage of associativity, and we can transform the code in the form shown over here, where you can see that the sequence of the add instructions in the second and the third place has been interchanged. As a result of this sequence can be computed in 2 execution cycles by issuing the first 2 instructions in parallel, because the first 2 instructions do not have any dependence here. Therefore, we can say that we have achieved the optimization by reducing the number of cycles to execute this code. So, as a result, we can say that the analysis of loop-level parallelism focuses on determining data dependence of some later iteration onto an earlier iteration. Such a dependence is referred to as the loop carried dependence. To conclude our discussion onto detecting and enhancing the instruction level parallelism, we have found that the greatest common divisor test is defined to find the existence of dependence, and the compiler techniques such as copy propagation and tree height reduction are used to eliminate dependent computations. Having discussed the detection and enhancing instruction level parallelism, let us start our discussion on to uncovering the instruction level parallelism. We have already discussed loop unrolling as the basic compiler technique to uncover instruction level parallelism. We have observed that the loop unrolling with compiler scheduling enhances the overall performance of superscalar as well as very long instruction word processors. The loop unrolling generates a sequence of straight line code, uncover parallelism amongst the instructions. Here, to avoid the pipeline stalls, the dependent instructions are separated from the source instructions by a distance in clock cycles equal to the pipeline latency of the source instruction. Furthermore, we have discussed that to perform the scheduling, compiler determines both the amount of instruction level parallelism available in a program as well as the latencies of the functional units in the pipeline. Continuing over this discussion, today we will discuss two new compiler techniques to uncover the instruction level parallelism. These techniques are referred to as the software pipelining and global code scheduling. The global code scheduling can be performed by using two different methods known as the trace scheduling and superblocks. We will discuss these techniques one by one. First of all, let us discuss what is software pipelining. Software pipelining is a technique where the loop is recognized such that the code for each iteration is made by choosing instructions from different iterations of the original loop. A software pipelined loop interleaves instructions from different iterations without unrolling the loop. Here, I will explain this to you with the help of this diagram here, where you can see that the instructions are chosen from different loop iterations, separating the dependent instructions within one iteration of the original loop. For this purpose, let us consider this example sequence. This sequence we have already considered while talking about loop unrolling. Here in this example program, we are adding a constant f2 into an array through R1. Here in this particular example code, for software pipelining, the compiler symbolically unroll the loop. Here you please note that it is symbolic unrolling, not the actual unrolling. The compiler symbolically unrolls the loop and then it schedules the instructions. After symbolic unrolling, the compiler selects the instructions from each iteration which do not have dependence among each other. However, in this particular case, the overhead instructions such as the add immediate and branch not equal, which are used to evaluate the condition, they are not replicated over here. For this purpose, let us have a look onto this program sequence where the body of symbolic unrolled loop is shown having 3 iterations. That is, from the first iteration, the store instruction is selected. From the second iteration, the add instruction is selected. And from the third iteration, the load instruction is selected. The selected instructions from different iterations are put together in a loop with the loop control instructions as shown in this sample sequence. Over here, you can see that in this, the first 3 instructions are obtained from 3 iterations, whereas the branch evaluation and branch instructions, they are placed at the end of the sequence. Here note that for startup and finish up, we need some code that have not yet been executed. As you can see from this symbolically unrolled sequence, for startup, we need to run 2 instructions from iteration 1 and 1 instruction from iteration 2. The 2 instructions from iteration 1 are the load instruction and add instruction, and the 1 instruction from iteration 2 is the load instruction. Similarly, for finish up, we need to execute 1 instruction from iteration 2 and 2 instructions from iteration 3. The instruction from iteration 2 is the store instruction, and the instructions from iteration 3 are the add and store instructions. This loop takes 5 clock cycles to execute per result. However, the load and add are separated by offset of 16 here to run the loop for 3 iterations. That is 2 iterations less than simple loop unrolling and scheduling case. Here the registers F4, F0 and R1 are reused as there is no data dependence in this case. Thus, it avoids the write after read hazard. Now, with this much introduction to the software pipelining, let us compare the performance of software pipelining with respect to the loop unrolling. The software pipelining can be thought of as symbolic loop unrolling because here some algorithms use loop unrolling technique to software pipeline the loops. Furthermore, software pipelining consumes less space code as compared to loop unrolling. It is quite obvious from our earlier example of loop unrolling and the code which we just discussed for software pipelining. Furthermore, software unrolling reduces the time when the loop is not running at peak speed. It reduces it to once per loop at the beginning and end. For example, here in this particular case, if a loop is to do 100 iterations with 4 iterations symbolically unrolled, then we pay overhead for 100 divided by 4, that is 25 times, instead of 100 times as in the case of loop unrolling. This is shown below with the help of this figure. Here you can see that the symbolic loop unrolling fills and drains pipe only once per loop, whereas the loop unrolling fills and drains pipe once each unrolled iteration. So you can see the difference between these two operations, which shows that the performance of software pipelining is better as compared to loop unrolling. Now, with this much discussion on to the software pipelining, we will discuss a new scenario which deals with the global code scheduling. We have observed that the loop unrolling and code scheduling, it works well when the loop body is a straight line code, and at the same time the software pipelining works well when the body is a single basic block, as it is easier to find repeatable codes and schedule it. Whereas a global code is one where loop body has internal control flow also. That is, a loop comprises conditional blocks such as if, then, else, or for loops, etc. Here the effective scheduling of such a code is complex because it involves moving instructions across the branches into the shortest possible sequence to compact a code segment. A global code involves both the data dependence and control dependence. Hence, in order to enhance the instruction level parallelism in global code, the loop unrolling and scheduling or software pipelining approaches do not work efficiently. These approaches are suitable to enhance instruction level parallelism in straight line or single basic block codes. Now we can see that the internal codes of the loop have data dependence as well as the control dependence of the loop, and let us see that how we can overcome both by using loop unrolling. The most commonly used compiler-based approach for global code scheduling are the trace scheduling, which is also known as the critical path approach, and the second one is superblock approach. Here, before we discuss any one of these techniques for global code scheduling, let us first of all familiarize ourselves with the complexities of scheduling, the assignment instructions internal to a loop in a conditional branch of the global code. For this purpose, let us consider a typical global code fragment represented here with the help of a flowchart. This fragment represents an iteration of an unrolled inner loop. Here, moving, that is scheduling prior to the condition evaluation, the values of assignments to B and C, it requires much more complex analysis. Effective scheduling of this code may require moving assignments to B and C prior to condition evaluation. Particularly, before movement of B, we must ensure that both the data flow and exception behavior is changed. To see how compiler ensures the data flow, let us have a look onto the code sequence which can be written for this code fragment, flowchart showing over here. The code sequence shown over here is represented corresponding to each part of this fragment. The first part of the code corresponds to initializing the array and performing the addition operation, whereas next is the implementation of the control instruction, and then following code represents the assignment operations. Let us see the effect of moving assignment to B before branch not equal. Here, if B referenced in X or after the if statement, then moving B before if will change the data flow. This can be overcome, however, by making a shadow copy of B before if and using the shadow copy in X. However, such a shadow copy is avoided as it slows down the program. Similarly, we can see what happens when we want to move the assignment to C before the first branch. This is much more complex as compared to the previous movement. Here you can see that this movement requires two steps. In the first step, the assignment is moved over the join point of the else part, that is in the portion of then part. This movement makes instructions for C control dependent and is not executed if the else path is chosen. Hence, to ensure correct execution, a copy of instruction is made in the else part. The second step is if C assignment is moved to before the if test, provided it does not affect any data flow, then the copy of instruction in else part can be avoided. This above discussion reveals that global code scheduling is an extremely complex problem, and we have to look into certain techniques to simplify the complexities of global code scheduling. In order to simplify the complexities of the global code scheduling, We will now discuss two different methods. These two techniques, they rely on the simple principle that focus the attention of the compiler on the straight line code segment that is estimated to be representing the most frequently executed code path. So, based on this basic principle, let us first of all discuss the trace scheduling technique. The trace is a sequence of basic blocks whose operations could be put together into a smaller number of instructions, whereas the trace scheduling is a way to organize global code motion such that the cost of code motion is incurred by the less frequent paths. Trace scheduling is useful in case of processors having a large number of issues per clock, under the condition that conditional or predicted execution is inappropriate or unsupported, and simple loop unrolling is not sufficient to uncover the instruction level parallelism to keep the processor busy. Now let us see how we can perform the trace scheduling. The trace scheduling can be carried out in two steps. The first step is known as the trace selection, and the second step is known as the trace compaction. Trace selection is the process to find likely sequence of basic blocks whose operation could be put together into a smaller number of instructions, whereas the trace compaction is a method to squeeze the trace into a small number of wide instructions. So let us discuss in details the trace generation. For trace generation, as the probability of loop branches taken is usually very high, so trace is generated by loop unrolling, assuming branch taken. Additionally, static branch prediction is employed as taken or not taken to obtain straight line code by concatenating many basic blocks. For this purpose, let us have a look onto this flowchart which shows how a trace can be formed. Here you can see that this flowchart is generated from our earlier global code fragment. Here, if we take the true path as most frequent, then primary trace could be generated by unrolling the true path for n number of times. We can assume n is equal to 4 as a typical case. Here we have shown 2 blocks, but this is to be extended for 4 similar fragments. Here you can see that the trace exit is jump off the frequent path and trace enter is return to the trace. The second step for the trace scheduling is the code compaction. The code compaction is basically the code scheduling where the compiler attempts to move operations as early as it can in a sequence that is the trace, and then it packs the operation into a few wide instructions or issues packets as possible. Trace scheduling basically simplifies the decision concerning global code motion. Here, branches are viewed as jump into at the trace entrance point or jump out at the trace exit point at the selected trace, which the most probable path is. Here note that when code is moved across trace, additional bookkeeping code may be needed on the entry or the exit point. Furthermore, when an entry or exit point is in the middle of a trace, significant overhead of compensation code and bookkeeping may be necessary. This makes the trace scheduling an unattractive approach. Furthermore, the drawback of a trace is that the entries into and exit out of a trace in the middle of a trace causes significant complications, and compiler requires to generate and track the compensation code. This drawback is overcome by using another technique known as the superblocks. Now let us talk about the superblocks. Superblocks are a form of extended basic blocks which have a single entry point but allows multiple exits. Therefore, it is easier to compact superblock as compared to a trace. In our earlier example of global code, superblocks with one entrance can be easily constructed by moving the assignment C as shown here in this figure. Here, tail duplication is used to create a separate block that corresponds to portion of the trace after the entry. Each unrolling of the loop creates an exit from the superblock to the residual loop that handles the renaming iterations. Here you can see that the residual loop is associated with the superblock exits corresponding to the false condition. Here this residual loop handles the iterations that occur when the unpredicted path is selected, which means that if the unpredicted path is selected for n is equal to 1, then the remaining iterations, in this particular case, the remaining 3 iterations are taken care of by the residual loop. Similarly, if the exit path is selected at n is equal to 2, the residual loop take care of 2 iterations and so on. With this much discussion about the superblocks, let us see the advantages of using superblocks. Firstly, you can see that this approach reduces the cost of bookkeeping and scheduling as compared to the general trace generation and trace scheduling. Furthermore, its code size may enlarge more than the trace-based approach, but its complexities are less. Like trace scheduling, superblock scheduling may be most appropriate when the other techniques fail. Now, with this much discussion about the software pipelining and global code scheduling, we have in fact discussed in detail 4 different approaches for uncovering the instruction level parallelism. These techniques include the loop unrolling, software pipelining, trace scheduling, and superblocks. All these techniques aim at trying to increase the amount of instruction level parallelism which can be exploited by a processor issuing more than one instructions in one clock cycle. Now, we have in fact described different techniques for exploitation of software-based instruction level parallelism. With this much discussion onto different techniques for instruction level parallelism uncovering, let us consider some numerical examples based on whatever we have discussed in the previous two lectures and in the today's lecture. For this, let us first of all consider this numerical example. Here, for the program code given, you are required to find out all types of dependencies, that is, what are the output dependence, anti-dependence, and true dependencies in this code. Please also indicate whether the true dependencies are loop carried or not, and also comment upon why this loop is not parallel. Here you can see that this for loop starts with I is equal to 2 and it ends for I less than 100. This loop consists of 4 statements, S1 through S4. Here you can note that there is an anti-dependence existing from S1 on A, and there is a true dependence from S2 to S1. Here the value of A in S2 is dependent on the result of A in S1. That is, in the second statement, it is depending onto the first statement. Similarly, there is loop carried true dependence in the 3 statements as from S4 to S1 on B, S4 to S3 on B, and S3 to S3 on B. And similarly, there is a loop carried output dependence from S3 to S3 on A. While considering the second part of the problem, where we have to indicate whether the true dependencies are loop carried or not, we know that for loop to be parallel, each iteration must be independent of all others. Whereas here in this case, the dependencies 3, 4, 5 are true dependencies, and they cannot be removed by renaming or any such technique. Thus, these dependencies are also loop carried dependencies, as the iterations of the loop are not independent. Lastly, these factors imply that the loop is not parallel as the loop is written. Loop can be made parallel by rewriting the loop to find the loop that is functionally equivalent to the original loop that can be made parallel. And this you can try by rewriting this loop and find out a new sequence of the loop. Now let us consider another example. Here you can see the loop given below, which is used to find the dot product, assuming that the running sum of F2, which is initially 0, and it contains recurrence. Assume the pipeline latencies from the table shown over here and 1 cycle delayed branch, and considering the single issue pipeline, you find out unrolling the loop sufficient number of times to schedule it without delay. And please also show the schedule after eliminating any redundant overhead instruction. Here you can see that this code has a loop carry dependence from iteration I to I plus 1. That is 2 subsequent iterations. They have got a loop carried dependence. It also has high latency dependence within and between the loops. Now if we unroll the loop twice in order to avoid any delay, we will get this following resultant code. Here in this resultant code, you can see that the multiply instruction has been moved at 4th place instead of at the 5th place, just to take care of the latency of the load F4 at R2. Similarly, in order to take care of the latency of 1 in the load F8, the second multiply instruction is placed after the add instruction, whereas the add instruction is purposely placed here in order to take care of the latency of 3 from the multiply instruction. So this way you can see that here the dependence chain from one add to the next add forces a stall. Similarly, in order to unroll further to schedule eliminating the stall, which is an overhead in this case, we take advantage of commutativity and associativity of the dot product of 2 running sums in the loop, one for even elements and the other for the odd elements, and we combine the 2 partial sums outside the loop body. This results in this code shown over here, which avoids the stall operation. Here you can see that the second add instruction, which is the add D instruction, it is placed in the second last position in order to take care of the latency of 3 from the multiply F6, F6, F8 instruction. Here the code assumes that the loop executes a non-zero even number of times, and the loop itself is stall free, but there are 3 stalls when the loop exists. This loop body takes 11 clock cycles. Now, with this much discussion and considering these examples, we conclude our today's lecture, and next time, inshallah, we will start with the other methods for uncovering the instruction level parallelism. Till then, Allah Hafiz.